In electronic engineering, we use mathematics to describe the physical world, so we can build models and solve real problems. That's why having a solid grasp on the fundamentals is so essential. To help us on this journey, we are going to use GeoGebra, a powerful tool that you can either use right in your browser online or download to use completely offline. Let's look at some foundational geometry basics. Before we can understand how electricity moves in waves, we need to master the basic language of geometry. To do that, we are using a powerful, free tool called GeoGebra. We think of GeoGebra as a dynamic maths playground. In traditional maths, static formulas are written on paper, but in GeoGebra, changing a number instantly updates a shape, and moving a shape instantly recalculates the numbers. Let's set up our workspace so you can follow along easily. Now that we know what GeoGebra is, let's take a quick tour of the interface so you know your way around. As you can see here at geogebra.org/calculator, the workspace is divided into a few key areas. In the top left, the main menu handles the file options, like saving and exporting, while the settings icon on the right lets you customize your grid, access, and app preferences. On the left sidebar, you'll find the algebra view to manage your objects and see their values, the tools view for geometric construction, and the input bar at the top for typing commands and functions directly. The large grid on the right is your graphics view, where all your geometric constructions and plots happen. And you can use the zoom controls on the bottom right or the virtual keyboard at the bottom left for special mathematical symbols. Okay, looking at the actual GeoGebra application, we have two versions, the one offline and the one online. There's a slight difference in how the settings are handled. It's all the same, but it's just in different locations. So this is the offline version. So if I click on settings, you can see I can immediately change the grid types. So those settings can be changed. If I say open settings, it allows me the different tabs, the grid, the X to Y axis. And if I go down, I can also see that there are some settings on the algebra side where, for instance, I can change the angle units. I can change from degrees to radians over here. Okay, so all the settings on the right. On the bottom right, we will get the zoom in and zoom out and home. I can also zoom in and out by using the center mouse scroll wheel. Okay, if I want to pan, I use the left click button on the mouse. I can pan, and on the left you will see right at the top the main menu. If I click that, I can clear everything, or I can open, you can save to your computer, or you can export. I also have the algebra view. If I click that, you can see that the input bar disappears. And my tools view, I get all the basic tools. If you scroll down, you'll see more tools. If you click here, so algebra view, and then on the left, we'll see also that we've got our virtual keyboard. So with different inputs that we can pick up from here. If I enter something, I just type. So if I say, for instance, say A equals 1, so that gives me a constant value of 1. It's case sensitive. In other words, if I say a small lower letter A is equal to 1, that's actually two different values. I can also use the underscore, which is handy. So if I say A underscore 1 equals 3, then that defines it as well. If I want to change or delete, I use my ellipses on this side, the 3 dots. So I click there, I can then just say delete. Or if you wanted to change something there, you can go to settings. It'll open settings on the right. There I can change the name, the definition, labels, captions, color, whatever you want to do over there. Okay, so if I wanted to, say for instance, add an angle, I'll go to my virtual keyboard. I will go to my Greek letters. I can use maybe alpha. And if I say alpha equals like 45 degrees, GeoGebra will assume that this is in radians, except if I tell it it is in degrees. So to do that, I press Alt and O, and it adds the degree sign there. So now GeoGebra knows I'm talking about 45 degrees. Okay, so in general, we've got the graphics view on this side, we've got the algebra view, the tools view, the virtual keyboard, the zooming, and all the settings. And then obviously if I want to clear everything, clear all, I can either save it or I can just discard and I can start from scratch. Now let's look at our first fundamental shape, which is the circle. A circle is defined by three simple metrics. The radius is the distance from the exact center to the outer edge. The diameter is the distance straight across the circle, passing directly through the center. And naturally, the diameter is always exactly twice the length of the radius. The circumference is the total boundary length if you were to unroll the circle into a straight line. An arc is defined by two distinct points on the circle boundary. For thousands of years, mathematicians noticed something incredible. If you take the circumference of any circle of any size, shown here in green and indicated as capital C, and divide it by its own diameter, shown in red and indicated as D, you always get exactly the same number. That universal constant is called pi, which is roughly 3,14. Because it is a constant, the Greek letter pi was assigned to this number, and it is fundamentally just a ratio. So, if anybody asks you what is pi, you can say it is the constant value we get when we divide the circumference of any circle by its diameter. Because it's a fixed ratio, it means that if we know either the circumference or the diameter, we can easily calculate the other. Building on what we just saw, let's look at what happens when we use the radius instead of the diameter. As you can see here, the red line now represents r for the radius, which is simply half the diameter. Because a full diameter is made up of 2 times the radius, if we take the circumference and divide it by the radius instead, the result is double our previous number, exactly 2 pi, or about 6,28. This naturally leads us to one of the most useful formulas in geometry. Because the ratio of the circumference to the radius is 2 pi, it means if you want to find the circumference of any circle, you just multiply 2 times pi times the radius. Let's prove all of this visually in GeoGebra. We are going to use GeoGebra to look at the important characteristic of a circle, which is its ratio of the circumference divided by the diameter. To do this, I'm going to start with a center point A, which I'm going to place at the center 0, 0. So that places point A in the middle of my Cartesian plane. I then define my radius. I'm going to call it r equals to 1. And then the diameter, I'm going to call that d equals 2 times r. Okay, so I have my center, I have my radius, and I have my diameter. Now I want to draw the circle. I'm going to call it C equals circle. I'm placing it at center point A and the radius r. Okay, so that shows me the circle, the center point A, the radius of 1, and now I want to determine my circumference. So now I'm going to call circumference capital C equals circumference of C. Okay, so it gives me the value 6,28 for that distance. Now I want to work out the ratio. So I say ratio underscore of D, because it's going to be my circumference divided by my diameter, and I can see that value is 3,14. Now I also want to work out the ratio of the circumference relative to my radius, and I can see that it's 6,28. So it's double that. You can see also GeoGebra picks up that this is something it recognizes. So if I click on that, it shows me 2 pi. Okay, so 2 pi means that if we define this 3,14 as pi, then obviously this is 2 pi. Okay, so now the thing that we want to see is if I change the radius, what happens to these values? To change the value of r, I need to create a slider. So I click there, create a slider. It automatically places the range -5 up to 5. I want to change that, so I'm going to click -5. I make that 1, and I make that 10. I want to change the step. So I'm going to change it in steps of 1. Yeah, so there's my radius. So if I change my radius, my whole circle changes as well. I can see the radius changes, the diameter changes, but what does not change is my ratios. Can you see therefore, doesn't matter the size of the circle, the ratio of the circumference relative to the diameter, and also the circumference relative to the radius, that doesn't change. That's fixed. So that's a constant. So it doesn't matter what size circle you have, this ratio is always 2 pi. Okay, so 2 times pi is what we work with. So we say this distance divided by that distance is 2 pi. Next, we want to see how can we relate this ratio to actual angles. We are going to do that by starting with a point A at the origin again. So I'm placing A at 0, 0. I'm going to use r equals 1 as the radius. I'm going to declare a point B, which is at point R and 0 on the y-axis. And from that, I want to use the angle now. So I'm bringing up the virtual keyboard. I get alpha, and I'm going to say equals 1 degree. I want to make it degrees, so I'm going to press Alt and O, making it 1 degree. I want to create another point C that I want to be able to rotate it about point A, starting from point B. So I call that my point C, and it's equal to rotate, and it starts at B, rotates at angle alpha, and it is about A. Okay, so there's my point C. So if I want to rotate this, I need to make my alpha a slider. So I create the slider, 0 to 360 degrees. So if I move the slider, can you see there my C is rotating from point B back to point B all the way around. So if I zoom in, I've got a circle movement around A from B all the way around back to B. So if I want to track this angle, I'm going to say, well, let's call it angle, and use the function angle between B and C, capital C. Okay, so that gives me the same angle as this. So this is just verifying that when I'm rotating this, can you see there's the angle and it's increasing, increasing. I'm just going to take the angle, move it out of the way so we can watch it. So that angle is the same as this angle. So this is the one I'm changing. This is the one I'm measuring. I'm saying, what is the angle between these 2 points? So it's a line here and a line there. What's the angle between them? You can see there we're sitting at 90 degrees. There we're sitting at 180 degrees, 270, and just before it's 360, it goes to 0. Okay, so all the way around. Okay, perfect. Now I want to create an arc. So the arc will be the part of the circle that goes from B to C. To do that, I'm going to call it my arc 1, and it's equals to circle arc, and that is from point A, B, and C. There's my arc. Okay, so now if I change my angle, I see I'm drawing an arc. That's perfect. So I want that length. It's actually giving me the length, but I just want to make sure that I've got the right length. So I say D is equal to the length of arc 1. Okay, so it should give me the same value. So that's the length of arc 1. So I want to work out the ratio between my arc length and my radius. So to do that, I can go and I say ratio relative to my radius is equal to the arc length, which I'm going to call plot, let's use D, divided by R. Okay, so there's my arc length. So if I go and I move all the way to 180 degrees, can you see something familiar? 3,14. Okay, so that is pi. If I move all the way around just before 360, because it's going to disappear when I get back to 0, I can move it slightly up using my arrow keys. There's 359. Can you see? Hey, there's 0 again. I can slightly move it up. When I hold in shift and up arrow key, I can move it there. You can see that's 2 pi. Okay. So this shows me that the arc divided by the radius gives me something that relates to angles. So I know these angles because we know this is 90 degrees and halfway is 45 degrees. This is 180, 270, all the way back to 360. But what I see is I can use the fact that this distance divided by this distance is also a constant. And that gives me my angle in radians. So if I want to prove this, I can say that my angle in degrees is equal to the ratio relative to my radius divided by pi multiplied by 180 degrees. Okay, so that calculation, I divide that with pi multiplied by 180 and I get exactly what I'm getting there. You see, so that is my relationship between my angle in radians and degrees. And you can see the arc length divided by the radius gives me that, and I can convert it back to something that I understand. Okay, so if I wanted to see how this works, so let's go to 180 degrees and I change my radius. So now same thing, go to my radius, I say let's create a slider, and we make it 1 to 5 is fine again. Let's take the step 1 again, and then we see what happens with this ratio if I change the radius. So that should increase my circle. Can you see everything changes, but the ratio remains the same? It's saying that the arc length divided by the radius is a constant. Okay, so that's very handy. So if I change my angle, I make it maybe, say for instance, 90 degrees. I can see I'm sitting at 90 degrees. There's my ratio, actually the angle in radians. And then if I change my radius size, you can see it stays the same. Okay, so that's a very handy relation I can use. There's a relation between the arc divided by the radius, and that gives me the angle in radians. The next fundamental shape in geometry is the right-angled triangle. A right-angled triangle is simply a triangle in which one angle measures exactly 90 degrees. Because of this special corner, it unlocks some of the most powerful rules in mathematics, rules that engineers, architects, and animators use every single day. Before we do any maths, let's learn or revise the names of the sides because they matter a lot. The hypotenuse, this is always the longest side, and it sits directly opposite the 90-degree right angle. The other two sides from the right angle itself are called adjacent and opposite sides. Now, here is the most common trap people fall into. The opposite and adjacent sides are not fixed. They are completely relative to which angle you are currently looking from. Take a look at this illustration. On the left, our character is focused on angle alpha, down at the bottom left. From this perspective, the blue vertical side is opposite across the angle, and the yellow horizontal side is adjacent, right next to it. But look what happens on the right when we shift our perspective to angle beta by flipping over the triangle to the right as we moved our viewpoint. The side roles flip. The previous vertical side becomes the adjacent, and the previous horizontal side becomes the opposite. Notice that the hypotenuse never changes. It is always the longest side opposite the right angle. The Pythagorean theorem applies only to right-angled triangles. It states that the square of the longest side, the hypotenuse, is equal to the sum of the squares of the other two sides. That means that the length of side C is equal to the square root of A squared plus B squared. Let's investigate this using GeoGebra. We are going to draw the triangle using vectors. We do that by starting with point Q equals position x1, y1. Then we are going to create vectors that point in the x and in the y direction. So I'm starting with vector A equals, and I call it vector, and then where it starts is position 0, 0, and it goes to the x position of Q and y0. Okay, so there's my first vector A, starting at 0, pointing to the x coordinate of Q and y equals to 0. The next one, B, you can see B starts at this position, which is the x position of Q. So I'm going to say B equals also a vector, and it starts in the x position of Q, y equal to 0, and it goes all the way to the x position of Q and the y position of Q. Okay, so I'm going to zoom in. There's the B, there's the A. So I'm saying the B vector, it starts here, and this is the x position of Q, and y is equal to 0, and it ends at the Q position, so the x position of Q and the y position of Q. Now C, I want to draw from 0, 0 up to Q, so I'm going to say C equals a vector, and that I can just say is Q. So it starts at 0, 0, ends at Q, so there's my triangle. So I'm going to now determine the length of each. I know this is 1 at the moment, so I'm going to say A, capital A, is equal to the length of A. You can see that's a 1. You can say B equals the length of B, and then C equals the length of C. Okay, so this calculates the length of each one of these. So if I move my point around, can you see that my x coordinate, which is A, and my y coordinate, which is B, changes correspondingly. So there's my A2 now, and my B also 2. Okay. So now I want to use Pythagoras to say C underscore calc, which is the calculated value, is equal to SQRT, and once I do the bracket, it recognizes it as the square root symbol of A to the power of 2 plus B to the power of 2. Okay, so there I get my Pythagoras. It gives me exactly the same value as the C, which is the actual value from GeoGebra. And if I move my Q point around, thereby changing the X and the Y coordinates, I can see that calculating the C is exactly the same as the length of C. Okay, so that just proves that my Pythagoras shows me the relation between the hypotenuse, the two right sides of the right angle. Trigonometry literally means triangle measurement, and it's from the Greek trigonon and metron. Many people find trigonometry intimidating because of words like sine and cosine. But here is the big secret. Trigonometry is not about complex equations. It is simply about ratios, comparing the size of one side of our triangle to another. When we ask, what is the sine of our angle? We are simply asking a comparison question. What is the length of my vertical opposite wall divided by my diagonal hypotenuse for that specific angle? If that ratio is, for example, 0,5, it just means that the wall is exactly half the length of the diagonal, the hypotenuse. Cosine is the exact same concept, just comparing the horizontal adjacent floor to the hypotenuse. Let's explore these custom math fractions or ratios in GeoGebra and see how they match up perfectly with the built-in trigonometric functions. We use our previous triangle now to look at the relations with the angles. So we'll just paste in here the definitions, which we'll put on the side. You can see there's normal text, adds 2 points. I can switch off the points. Normal text gives me the definitions. What we need to find now is the angle between these two lines. So we know this is vector A, this is vector C. So to find the angle, I go to my input bar, I select my virtual keyboard, I say alpha is equal to the angle between vector A and vector C. And we can see that that is 45 degrees. Now, if I want to work out the sine, which is then calculated by GeoGebra, I'm going to say sine underscore actual is equal to the sine of alpha. Okay, so I'm working out the sine of alpha. So that gives me 0.7071. Now, if I want to calculate this, I'm going to say sine underscore of my ratio is equal to, according to this, the B divided by C. So there's my B divided by C. And here you see that it's the same. So the sine of that angle is actually just the ratio this length divided by this length. So if I want to interpret this, we can see that if you have the angle and one of the sides, you can calculate the third, which is very handy for us. Now, if we take something like this specific example, I take my calculator and I look at my C value is 1,414, actually comes from the square root of 2. So I've got 2, square root of that is the same, and I multiply that by the sine of the angle. So the angle is 45, the sine of 45, so it's the square root of 1, which is my C value, and I'm going to multiply that by 0.707, and that is equal to 1. So that tells me that if I have this multiplied by the sine of this, I can get that. Okay, it's very handy tool. So I can now also move this point to look at the angle 45. I know that this length and this length must be the same. So if I go 2 on the x, I go 2 on the y, and it's still 45 degrees. Now, what I've seen here now is the length of C doubled. So I've got twice that length. So if I do the same calculation, I say that I've got the square root of 2 times 2, because it's twice the length. You can see there the C length and that length is the same. And I multiply that by the sine of 45 degrees. So that gives me 2. So I take that length multiplied by the sine of this angle, and it gives me the length of 2 for B. Okay, very handy. So if I want to do the same for cos, let's just go back to a normal 1 by 1. I can say that cos of the actual is equal to the cos of my angle alpha. Okay, in this case, it's the same value. And then I'm going to calculate cos. So cos for my ratio is equal to, and if I look at my cos definition, it's the adjacent A divided by hypotenuse C. So now that is A divided by C, which gives me the same value, which is now, because I have 45 degrees, but once I change the X and the Y to be different, you can see that the cos is tracking the actual cos, and the sine is tracking the actual sine. Okay, what we want to do is now to take an angle of 30 degrees. So if I have 30 degrees, I know that I change this coordinate to the square root of 3. Okay, there's my 30-degree angle. Now that 30-degree angle gives me the sine value of 0.5. So interpret that, it means that this length is half of that length. Okay, and I can also calculate that. So I'm saying that my length for C is 2. So I've got 2, and I'm going to multiply that by the sine of 30. And that is equal to 1. So here you can see B is 1, B is 1. So works out perfectly. You can see that this is just ratios between the sides and the angles, and that's what makes it so handy. So here is the big secret. No matter how big or small you draw your right triangle, if the angle stays the same, the ratio between its sides never changes. It's locked in as a constant. So when we talk about the sine of an angle, all we are really asking is, what is that constant ratio for that specific angle? Think about it. What is pi? Just a ratio. What is sine, cos, or tan? They are all just ratios. For this video, the only objective is to ensure that the concepts are understood and visually applied. We are going to apply this knowledge in the next videos, so don't worry too much about where all of this is used. That is coming next. Okay, I hope you find this helpful.